Hi, everybody. Last examples of the day. We're going to be going over some gas stoichiometry problems. Now, if you recall, stoichiometry means converting something into something else. So we're still going to be using equations. We're still going to be balancing those equations. We're going to be using mole ratios, but we're going to be involving gases and the relationship between volume and moles of a gas into our calculations. Now, there's a couple different ways that we can set these up depending on what the problem is asking us for. So we're going to go over two different types of problems just so you have one of each as an example to base your other problems off of. Now, I do have to mention in the Go formative, for some reason, at least on my computer, all of the arrows in the documents have been converted to little boxes in the balanced equations. So I'm not sure why, but I am going to attach all of these worksheets to Google Classroom as well, so you have hard copies of everything beyond just in the Go formative. So if you're looking at that and you're like, I don't know what that symbol is, it's supposed to be an arrow. I couldn't get it to change. I'm not sure what happened. So if anybody has some tips for me on formatting, feel free to send me some help. All right, so we're going to go over number one on the gas stoichiometry worksheet, and this is number one for everybody. It's gives you an equation, C2H6 plus O2. So I'm just going to write this down. Forms CO2 plus H2O. And if you remember, that is an example of a combustion reaction. We're going to start by balancing it. So I am going to 4, 6, 7, balance it real quick here for you. 4, 6. And here is the balanced equation. 2C2H6 plus 7O2 forms 4CO2 plus 6H2O. We had to double the coefficients because we had that weird number of oxygens on the product side. We had to get it to an even number by doubling everything. Now, the first part of this problem says how many moles of CO2 are produced when 2.09 moles of ethane are burned. So we're going to be just doing a mole to mole calculation. 2.09 moles of ethane, that's C2H6, over 1. And we want to convert this to moles of CO2. So we're going to use our balanced equation to do that. We want to get rid of ethane. So 2 moles of ethane is going to go on the bottom. And let's see, we're looking for moles of CO2. So 4 moles of CO2 on top. That's the setup. Do your math. And that's going to give you 4.18 moles of CO2. Okay. That's just a review of what we've already done. So everybody should be familiar with that. That's a mole to mole calculation from our stoichiometry unit. Now, if you go on to the next problem, C8H18, you'll notice that the units used in the problem are volume units rather than moles. So again, I'm going to balance my equation real quick here. These are going to be some big numbers. 2, 25, 16, and 18 are my coefficients. Now it says here how many liters of H2O are produced. So that would imply that water is in the gas state. When we're talking about volumes of combustion reactants and products, they're generally going to be in the gas state. How many liters of H2O are produced when 2.81 liters of octane are burned. So we're converting 2.81 liters of octane, C8H18, into liters of water. So if you're going from volume of one gas to volume of another, you're going to be using the same stoichiometric relationship we used in the last problem with the mole ratio. Instead of a mole ratio, it's a volume ratio, but moles and volume, if you recall, are directly proportional. So we can use the same mole ratio from our balanced equation. So 2 moles of octane is going to go on the bottom. And let's see, what are we looking for? Water, 18 moles of H2O is going to go on the top. And when we solve this problem, 2.81 times 18 divided by 2 gives us 25.3 liters of H2O. Same setup as last time, except we're using volume units instead of moles as our units. So there is no difference in the setup when you're going from a volume of one gas to a volume of another gas. This is the way that you would do it. Okay, you would use the same ratio from your balanced equation. All right, now going on to a problem that's slightly more challenging. Technical chemistry for you guys, this is problem number 3 on your gas stoichiometry worksheet. And honors, let's see, this is problem number 5 for you. We start off again with an equation to balance. H2 plus N2 forms NH3. So again, I'm going to balance this. Here's my balanced equation. It says, suppose we have a 12.2 liter sample containing 0.5 moles of hydrogen gas at 1 atmosphere and 25.5 degrees Celsius. If all of this hydrogen is converted to ammonia at the same temperature and pressure, what would the volume of the ammonia be? Okay, so let's first talk about what we're trying to find and what we're given and what we know and all those things that we always want to ask ourselves at the beginning of a calculation. We know this is gas stoichiometry. I told you guys it's going to be a little more challenging than the previous problem. So let's first figure out if we're starting with mass, moles, volume, what substance are we starting with, and then we'll go from there. It says we have a 12.2 liter sample, but it doesn't say what that sample is. So I'm going to ignore that number for right now until I get some more information. And then it says we have part of that sample containing hydrogen gas, 0.5 moles. So we know that moles is going to be N. So we have N equals 0.5 moles of hydrogen gas, H2. It's important that we label all of our numbers here because we're converting substances, we're converting units. We don't want to get confused. And I encourage you to go back and refer to the notes as we're going through these problems because the roadmap and some of the visuals will be helpful for you. All right, so N equals 0.5 moles of hydrogen gas at 1 atmosphere, so that's my pressure, and 25.5 degrees Celsius, so that's my temperature. In Kelvin, that's 298.5. If all of this hydrogen is converted to ammonia, what would the volume of ammonia be? So that means I'm looking for volume of NH3. This is what I know. I have my balanced equation. I know I'm starting with moles of hydrogen. I know I want to find volume of NH3. I know my pressure and temperature values. So now I want to go and refer back to my roadmap. I'm starting with moles and I'm ending in volume. So I'm going to take a minute to write out the roadmap. The new roadmap that was in the notes. Mass of A to moles of A to moles of B to volume of B. Now I'm going to cross off mass of A because I'm not starting with mass, but I am starting with moles. I'm starting at moles of substance A, 0.5 moles of H2. And I know that I'm trying to find volume of substance B. It's going to be some volume of NH3. So that means I have to convert moles of hydrogen into moles of NH3 first. That's the first step. Okay, if I'm starting here, I want to go to moles of B using my ratio. So I'm going to look back at my balanced equation. I'm going to start with 0.5 moles of H2. I'm going to put that over 1. And my first step is going to be a mole ratio. So going back to my balanced equation, I have 3 moles of H2. That's going to go on the bottom. So moles of H2 cancels out. And I'm trying to get to NH3. So 2 moles of NH3 is going to go on the top. Those numbers come right from my balanced equation. Now I have one more step. I want to get from moles of substance B to volume of substance B. So if you refer back to the notes, there were 2 ways to go about doing this. One way was if the problem stated that it's at STP, and then you can use 22.4 liters as a conversion factor between moles and volume. But this problem does not say that it's at STP. So we're going to stop here. We're going to calculate moles of NH3, And then we're going to go to the ideal gas law equation. And we're going to plug our moles in to the ideal gas law equation along with the pressure and temperature that we already know. And we're going to solve for volume of NH3. We have to do this conversion step first because we're converting hydrogen into ammonia, which is NH3. And we want to find the volume of ammonia, so it's important to do this conversion step. All right, so 0.5 times 2 divided by 3 is 0.33 moles of NH3, 0.33 repeating. So I'm going to be converting moles into volume. Now, if you recall, the volume was what we didn't know, but we did know pressure, temperature, and now we know number of moles. So we're ready to use the ideal gas law equation. We know pressure is, 1 atmosphere. Volume is what we're trying to find. We know moles is 0.33. We just calculated that. Because pressure is in atmospheres, we're going to use 0.0821 as the R value. And our temperature, 25.5, is 298.5 Kelvin. 298.5. Okay, so here's my work. I have pressure, which I know, times volume, which is what I'm trying to find, equal to N, which is number of moles, R, which is our constant, and T, which is our temperature. So I'm going to calculate the answer here, 0.33 repeating times 0.0821 times 298.5 divided by 1 atmosphere gives us a volume of 8.17 liters. So for that problem, we first had to convert one substance into another before we could use the ideal gas law to convert moles into volume. Okay, so you want to make sure you're watching your units. You want to make sure you're watching which substance is which, labeling everything. And as always, if you have questions, please let me know and attend our live chat session this week, and we can go over any problems that